All right. Welcome everybody. Welcome to this week's meeting. So just a few reminders. I'm recording the meeting, joining the Outlook and Google Groups. You guys already know about that. And the research proposal drafts. So the final proposal is coming up. I can talk more about that later. I'll be talking a little bit about some admin announcements, uh, the information retrieval exercise that we're going to be doing today, which is the third and final exercise. And then next week's meeting, it's Thanksgiving week, so we're actually not going to be meeting. And I have a reminder later. But yeah, so some reminders, or some announcements. Spring semester research and project showcase. So we actually updated our website, and if you check it out, now we have this Spring Clay 2026 competition page that if you go on ARC and you click on um, spring semester, you'll be able to see the page. And here it has all of the information that you need to know about basically joining us to do research in the spring if you'd like. And all I ask from you guys is to sign up using this competition sign up form. So I know it's another survey, but I promise this is probably the last one that we do. No more surveys after this, hopefully, which I know it can be a little annoying. But yeah, so it's this survey and fill it out. So it really just asks for your name, email, year of study, online or on campus, what classes you have taken, your timeline or time zone, and if you have participated previously, if you're a returning member, and also if you're interested in taking a CS 8903, the desired role, so either a lab lead or a lab member, and yeah, just click on which one you like. And what labs would you be interested in pursuing? And this is really important because this is going to determine how we do team matchmaking. Um, and also specify like if you have a specific task that you'd be very interested in pursuing here. So pretty straightforward form. Just as a reminder, so I have the link for both the website and also the form, but you can find everything in the website itself. The form is at the top, and then it has a bunch of information about basically what we do and what we're trying to do in the spring, which I think you guys kind of already know, but it does have some good information here if you want to recap. So I highly suggest for you to go through the web page, and then once you're done reading everything, fill out the form. The second announcement would actually be to see if there's any volunteers here that do live in Atlanta and they would like to come to the project showcase. So the Data Science Club is hosting a project showcase this Thursday. It's going to be at Klaus 1443, and it's going to be from 6:30 to 7:30 p.m. this Thursday. Do we have anybody from Atlanta or that lives in Atlanta here in the call? Okay. Pooja, you live in Atlanta or no?
Oh, yeah.
Yeah. Okay. So if you like to volunteer, don't feel any pressure, but I guess just doing a call out for everybody, especially the people watching if you're not in the meeting right now. If you're watching this and you are living in Atlanta and you'd like to come to the showcase and just talk about your experience joining the interest group or doing research with us in the spring, if you have done that. If you have not, it's totally okay. You can talk about your experience doing the interest group this fall semester, because I think this is the biggest group that we had so far for the interest group. I don't think the one last year was as big as this one. So if you like to come, and I think there's going to be food provided. So if you like to come and talk about your experience, that would be super welcomed. Okay. So today is going to be, like I said, the third and final exercise that we do, and it's all about information retrieval. So basically, the way this is a diagram that I took from the slide itself. So we're going to be doing the exercise on this data set, the Microsoft Marco data set, where we have a collection of data like a corpus, and we have queries, and then we're trying to find information in the corpus based on the queries. And basically, this is an information retrieval system. So for each query, we're going to search through all of the passages, and we're gonna return the most relevant ones. And this is something that is super cool that like search engines are trying to figure out since ever, or since the internet came out. And we're gonna be doing a little project on that today. So without further ado, what I'm gonna do is I'm gonna open up the web page here on the left, and I have a README file that I did it today. So if something is not clear and I'm going through things in the code, please feel free to let me know, because I think this would be not only helpful for you right now, but also the people watching. So, okay, before I start, does anybody has any questions? You can raise your hand if you do. Okay, no questions. So I'll just get started. So the first thing that we're gonna do is we're gonna set up our virtual environment, and there's gonna be the same thing as last time. And because I did set up mine on the temporary directory last time, so basically the way how it works is if you did install your virtual environments in your temporary directory, once the session ends, once your instance ends, the one that you requested, for example, I requested for 4 hours. Once those 4 hours is gone and the compute becomes available again for someone else to use, everything in the temporary directory gets deleted. So that's why it's temporary. We only store things that are not permanent. So the first thing that we did was we ended up, and you don't have to do this if you already have done it, but like we did it last time, we open up the bashrc file and we added this export temp dir um, um, command here, and mine I put here at the top. But make sure to do that, and then you just save the file, Command S or Control S, and then you have to source it. So I'll do like source dash bash rc. Oops, I wrote it wrong. Source bash rc, and you would reload the file. If you have done that one time, you don't have to do every single time that you log into the cluster. So you just have to do it once. The second thing that we're gonna do is I'm gonna create my virtual environment. Anthony made a comment, so we should maybe be careful with this because some folks would be tempted to run this on the login node, and that may not be a great idea. Yeah, I agree. Um, Only do this, what I just did, if you are running on a compute node. So
I
if
think
you, yeah, go ahead, Anthony.
I think maybe we shouldn't encourage people to export that temp dir directory, um, because it's defined if you're in an interactive session and it's not defined if you're in a login node. So the temporary directory should just be valid if you're in the right environment.
Okay. Is there any way for us to enforce this? Or I
Just
guess people would have to
don't add it.
know what they're doing.
Don't Yeah, just don't add it to your bash. Don't add it to your bash RC. And if people complain about the TM TMP dir like environment variable not being set, then that means they're doing it from the wrong environment.
Right. Okay. So you heard from Anthony. Don't copy and paste that export command into your bash RC. So I can actually do that right now on me. I can delete this. But since I'm running from a compute resource, you'd be fine. And then if I just source it, that's okay. And then I can cd into temp, and that's also fine. The SGT file, I'm just cd into the repo. Okay, so the first thing that we're gonna do is let me close everything and just have the terminal open. I'm gonna actually install the virtual environment in the temporary directory. So uv venv, and then I can actually do like this dash temp dash venv, and then I do source tmp dot venv, then activate. And now the virtual environment is activated. And then I'm gonna go to the project. So the project 3, if we go on the repo and we check for project 3 information retrieval, we're gonna see that we have a PyProject TOML file and also the information retrieval IPy notebook here. So I'm gonna be installing the project dependencies right now. So I'm just gonna go into cd projects 03. Let me clear this, and then uv pip install dash e dot to install the dependencies. And this should take a little bit of time, but hopefully not too long. I think Torch is going to take the most time. And then after this, we're going to create a symbolic link between the virtual environment that we just installed to our user directory on pace. So while this gets installed, does anybody has any questions? Okay, cool. It's done. Now we're gonna create a symbolic link to the venv that we just installed to our user directory. So what I'm gonna do is I'm gonna head to my user directory that I created, so my name, and I'm gonna create a symbolic link. So this is really hard to see, but I'm doing ln-s, which is this command here, and I can do dash tmp dot venv, and then I can do pwd and that venv. Cool. And if I do a ls-la, I can see that I created a symbolic link. Now venv, it's under my user directory right here. But the main location from venv is actually under the temp folder where we have created. Cool, so that's done. The second thing that we're gonna do, and for this project is a little different. We're gonna be running a library which is called PyTerrier, and the library needs Java to be installed in the system. So if we do Java dash dash version, we're gonna see that the Open JDK is already here, which is basically just means Java is already installed. But we're gonna be running some other commands here. So I've already ran those, but you can do it yourself. So the first thing you're gonna do, make sure you go to your home directory. You're gonna create this bin folder if you have not already. And then you're gonna install OpenJDK. You're gonna unzip the file, and then you're gonna export the Java home to the directory that we just unzipped. And at the end, once you follow everything, if you do uh, javac version, oh, not found. So in that case, I need to run this command right here, exports path java home. And if I run that command again, oops. Uh, what is happening here? I already have that on my bash.c file. So yeah, I have this here. Why is it not? Do I have to install this every single time that I? This is the
Are
first time
you
that I installed it, by the way.
uh
Do I have to unzip every single time? No, it's there.
what's wrong? You've exported Java home and you can't run
Yeah,
the Java C.
yep.
Um, can you uh echo like your path? No, echo $ path
Oh,
path. Yeah. And then look for the Java path should be in there, right?
yep.
Did you just edit your bash RC?
No, I did it before the call, but it was running fine.
Did you sourced the new bash RC?
I did, yeah. I can do it again.
Can you echo
Bash.c.
what Java home looks like?
Hang on just a second. Dude, it's gonna work now for no reason. Just because I source it?
Uh, your current terminal doesn't get the new bash RC like configuration edits until you either start a new session or resource it. So it might have been you edit it, but you didn't like refresh the terminal instance.
Oh, but that's weird because I did source the bash.c file previously, like early in the meeting. When I removed that line from bash.c, I sourced it and it was not finding it, but now it did, which is weird. But that's fine, I guess. Um, and then let me just check this again. See? And then when I activate the environment, oh, that's why I need to do that with the environment activated, huh? Okay, let's, I already have that. So let me cd bin tar export export source. I mean, that's already there. So Java. Okay, we're good now. I guess I had to install that in the vent. So okay, that makes sense. Okay, sorry about that. So make sure that you do this step once your virtual environment is installed to make sure that the Java C is actually running. But if you do type Java C dash dash version and you get this is what you should be seeing. Cool. So let me go back to the DS file here and let me open up the notebook. So this week's it's not Clay, the IGT file. project. So this week's notebook is on information retrieval. And what you're gonna do, you're gonna basically take the notebook, you're gonna copy, and then you're gonna paste under your user. So I've already done that, and I've already run the notebook, so I don't have to run again. But now that we have installed everything, we can actually take a look at the notebook. So this is actually quite a long notebook, and I'm not sure if I will have time to cover everything. Ritash made all of the notebooks, so big thanks to Ritash for making them. And I'm gonna try to go through as much as possible during the meeting today. But if I don't finish, then I think that's okay. You guys can do it as a take-home assignment, and then you can do the PRs, which is another thing that I wanted to talk about. Which, by the way, if you have submitted your PR so far, thank you so much for doing that. I have seen some really cool implementations of just people going above and beyond and implementing more models and doing hyperparameter tuning, all of that stuff. So that's really cool. But okay, the first thing we're gonna do, we're gonna make sure that we have the virtual environment running here, which we don't. So what I'm gonna do is Command Shift P and Python interpreter, select interpreter path, find venv bin, and then Python 3.9. Okay, and then venv is appearing now, so I can select that. And we're running on the venv. So that's how you do it. I don't have to run everything again because I already did, but there you go. So yeah, so the information retrieval, dense retrieval with FIs and narrow ranking. So today we're going to be doing all of those steps. The first one, we're going to be basically looking at this MS Markov dataset, which is real web search queries with relevance judgments. And then we're going to be doing a dense embeddings using narrow representations for semantic search. Then we're going to be using some algorithms like FIS and BM25, narrow ranking, PyTerrier, and then we're going to be doing a comparison between them, and then evaluation metrics at the end. And this is a very, very long data set, but notebook. But okay, so here we go. First step, we're going to be doing this two-stage retrieval pipeline. So stage one is going to be a fast candidate retrieval, so FIS and BM25, and it's going to retrieve the top 100 results. And the second stage is going to be an accurate re-ranking and cross-encoder and a final top 10 results. And basically, this is how Google and Bing and all of modern search engines work. And hopefully by the end, you get to understand a little bit more about information retrieval. So once you run the cell, you should see exactly this. You should see the Java home, you should see just the verification, and then you should get this Java C 17.0.2 version at the end. And then here we're just loading some dependencies, and we should see that we're running on CUDA, so make sure that you actually run the notebook on a GPU. The way to know that you are on an instance that is actually running on a GPU, if you type NVIDIA-SMI, what? How is this not working?
Are
Uh,
you not on a GPU instance?
I'm pretty sure I am. Let me stop sharing my screen just a second.
I think you do an LSPCI, I think should tell you like all the hardware devices attached.
It may have just
And
been a
NVIDIA,
typo.
NVIDIA. Hmm? Oh, it was a typo. Thank you.
Yeah.
Okay, it's Monday, guys. Sorry. Uh, NVIDIA-SMI, and you should see this. Okay, cool. Sorry about that. So if you do see this, it means that you do have a GPU attached to your instance. Okay, so second step, the Microsoft Machine Reading Comprehension dataset is one of the most important datasets in information retrieval. So there's some facts here why we're using it. but the example, so we're gonna have a query, and there's gonna be some relevant passages in the data set that we actually want to retrieve from the query. So what's the difference between a tornado and a hurricane? And then we're gonna get the main difference between a tornado and a hurricane is that a tornado forms over land, while a hurricane forms over water, and blah blah blah. So for this notebook, we're gonna be working with a sample subset just to keep things fast. So understanding the dataset structure, why using this dataset, it contains real Bing search queries that is paired with relevant passages for web pages. So each item in the dataset has a query, a passage, and this e-selected parameter or label. So a query is a search question. So how do airplanes fly would be an example. A passage would be multiple candidate passages or examples in the really big corpus of data that might answer the query. And then the label is going to show which of those passages are actually relevant or not. And is usually going to be like a 0 or a 1. 0 meaning it's not relevant, and 1 meaning it is relevant. So we're going to load the data set twice for different purposes. The first one is going to be, we're going to be extracting the passages from a corpus of text. So those are going to be documents that we're going to be searching through. And also we're going to be getting the query. So let me make this a little bigger for you guys. So we're also going to be extracting 500 queries, and those are going to be the search questions to test. And you can think of them like a library. So the corpus is going to be 10,000 books, and the queries are going to be 500 questions that the reader might have and might want to search in the books. And so we're going to be loading and inspecting some of them. So here we just a bunch of code to load the data set. So we have the corpus and queries. And then next, there's a bunch of print statements, but basically what we're doing, we're inspecting the dataset structure, showing one item from the corpus. And so here we have the dataset structure, keysing item, answer passages, query ID, query type. And then we have the first passage since 2007, the RBA's outstanding reputation, blah, 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 blah. And then we have some of the relevant labels and relevant passages. So 1 out of 10. And we see that only one of those passages are actually relevant. And we also have the labels, which is the ones that we're going to be using in this case, which is the e-selected one, is the one that we're actually going to be using. Yeah, so then we're just going to create a visual representation of basically what we're doing. So there's a bunch of code for doing that. We want to go through all of this, but this is basically the diagram that I showed previously that we have created. So the data set, and we have this process flow where in one side we have the corpus of the data set, and then we have the queries. And we're just doing some data processing here where we're creating a list of the passages, and we're creating a list of the queries. And then we're gonna create our information retrieval system here at the bottom. So yeah, some key takeaways: we load the same data set twice, different samples. From corpus items, we extract the passages, what to search, and then from the query items, we extract the queries, what to search for. And yeah, next, understanding the relevance. Not all passages are relevant. So here's just an example of the structure. So we have passage IDs you can think of, and we have the text and the e-selected and the status. So given the query, how do airplanes fly? We have 3 candidate passages. And we get the e-selected 100, meaning the only first one, the only first passage is relevant in answering that query. And that's how our data is. So it's basically labeled for us. You want to say something, Anthony? Or
Yeah. So one of the things about relevancies is that they're an annotation to the data set, and it's impossible to have a clean search data set right? So you have like millions of documents, and for any given query, it's impossible to have a set of documents that are to have all the full set of documents that are relevant. Like relevancy is kind of a subjective thing. And two, like you might be adding like new things to the system, and you don't necessarily know how to mark them relevant or not. So like if you have a data set like this, like when you pull queries into the system, like just because the annotation says it's like, this is relevant and this is not relevant, like the other thing that you have to consider is that the relevancy is kind of is like a limited by human annotation like time. So like things could still be relevant, but it's just the annotations don't exist for it to be relevant or not. Unless this is a clean data set that has been like annotated.
Super, yeah, like very much curated or something like that, right?
Yeah. A lot of real world like query data sets that you might find in Trek or Clay, they don't not every single item in the data set is annotated. So that's just the thing to be aware of.
Okay, that's good. That's cool. I've never done personally one of those information retrieval tasks, but yeah, this seems super interesting. I know that companies like OpenAI and even Google, they do like annotation parties where people just get together and annotate data sets. Um, but yeah.
Yeah, I mean this is also the thing that's the kind of the foundation of the reinforcement learning stuff that happens in large language models. Like you have some relevant signal on like whether one answer to a query is better than another, and so like you can use this to better push language models towards answers that are better. That's like a search problem, and this is kind of the way that you make search engines better is by providing more relevance and signals for like how to move towards being better.
For sure. Um, cool. Thank you so much for that. So I think what you're trying to say, the query relevance is this part right here, right? A mapping that stores which documents are relevant for each query. So yeah, thank you for addressing that. Um, so next we're going to be basically extracting those query relevancies and use them for evaluation metric later in the notebook. So that's what we are running here. And yeah, we just get those results. So the passages that were processed, 82,500 queries, and queries with relevance judgments are 490. So probably some of those, like Anthony said, probably don't have any relevancy. And next, we're just going to be displaying sample queries and some of the passages. So yeah, you have a little query, and then length of the query. And then you have a passage here at the bottom, which can have this text right here. And I can even do like a scrollable so you guys can see. So yeah, just a bunch of passages. So there are three types of muscle. One smooth muscle or involuntary muscle consists of spindle shaped muscle cells, blah, blah, blah. So those are just examples of passages, and those here at the top are queries. Okay, so number 5, why dataset statistics matter. Number 1, model constraints. So in binary models, they have a maximal sequence length, and the model they're going to be using, the multi-QA mini LM L6, has a max length of 620 or 512 tokens. So if passages are longer, they're going to get truncated and we're going to be losing information. So if most passages are 1,000 characters, but the model only handles 512 tokens, there's going to be a problem. And then there's a little example here. Number 2, performance and speed. So longer text equals slower processing. since the embedding of, for example, a 100-word passage is going to be fast, but a 1,000-word passage is going to be 10 times slower. So yeah, knowing the average length is going to help us estimate how long does the process would actually take. Number three would be understanding search behavior. So the query length tells us about search patterns. So short queries, once you through words like airplane and flights, this would be like mainly a keyword search. And long queries with more than 10 words, how do airplanes generate enough lift to stay in the air? So this would be a natural question, which funny enough, I think that once Google came out, people usually they used to search with long queries, and that was actually bad for Google. They actually wanted it was much better for them to for people to search into like short queries like airplane flights, blah blah blah, and they don't seem very connected, but that made things a lot faster for them. But now because of AI and they're like very interested into the types of things that people are searching so they can actually use that for their own training and for their own purposes, they want people to actually search like this again. And it's just something that I thought it was kind of funny how things are going back to long natural questions. Okay, so this is going to help us choose the right model and the right approach. Quality control. So statistics reveal data issues. So passages with 0 characters, data cleaning needed. Queries with more than 500 characters probably spam our errors. Like if we have a query that is very, very long, that is probably not a good query. And very short passages like fewer than 10 characters, they're not going to be very useful for retrieval because very rarely you can answer a query with 10 or fewer characters. And then some comparison baselines, know what's normal for your data set. So if retrieval suddenly slows down, check if the data has longer passages. And if the accuracy drop, maybe the queries are much longer, shorter than the training data. So yeah, data set statistics equals understanding while we're working on. So here we're just plotting some of the distributions of the passage length and query length distribution. So we can see that the length of the characters for queries, it's a little bit more than 30 characters for each query. And for the passages, the mean or the average, it's a little bit more than 400, but there's like this double distribution here happening where we do see a lot of passages that have about 300 characters and then it kind of drops. I'm not sure why, and then it pops back up again around 500 characters or so. Kind of funny. So yeah, so the average query length is 33 characters and the passage is 421 characters. Okay, number 6, dense embeddings for semantic search. Before I go into this one, do we have any questions so far of what we're doing, or do you guys have any questions? Okay, anybody would like to add anything to what I'm saying? Okay, I'll just keep going then. So the problem with keyword search, so traditional search methods like BM25 or TF, IDF, maybe you have taken natural language processing and you have seen those kinds of algorithms. They really rely on exact word matching, which was how things were done like way back in the day before we had embeddings and they were able to capture semantic meanings of words. But if we have query and the query is automobile repair, it's not gonna really match with car maintenance, even though those have like the same meaning, because they are or they have different words. So it will match automobile sales, which it does have the same word automobile, but completely different meaning. So we enter dense embeddings now, like basically what we're talking about. we're going to be converting the text into vectors that they capture the semantic meaning of the text. So we're going to go from similar meanings to similar vectors. And we saw this happening in the embeddings exercise that we did last week, where images that were semantically similar were clustered together in that latent space that we visualized, than images that were dissimilar, then they were farther apart. And the same idea happens with text. Once we convert text into this high dimensional vector, text that has similar semantic meaning is going to be close together in that latent space than text that has very dissimilar meaning. So yeah, automobile repair and car maintenance, they're gonna be very similar, even though the words are completely different, which is kind of cool. And yeah, this works across synonyms, paragraphs, or paraphrases and language. So how it works, we're gonna basically encode the queries and the passages into vectors. So depending on the model that you use, the vector length is gonna be different. So it could be 384 or 768 dimensions. We're gonna be measuring their similarity using cosine similarity or dot product. And we're gonna be retrieving the passages with the highest similarity to query. And then here we have some models. If you like, you can actually click through them, and it's gonna open up the, let me do here. So it's gonna open up the Hugging Face model card for that model, and you can check it out, what the model is. Maybe it has more information about what it was trained on and things like that. And some of those models, they even come with like the papers that they were implemented on. But we're going to be using the sentence BERT models, and specifically designed for semantic search. And they were pre-trained on millions of question passage pairs. They were optimized for retrieval tasks and basically provide fast inference, especially since we're using a GPU. So here we're just going to be loading our models. And in this case, we're going to be loading this model right here, the sentence transformers multi Q&A mini LM L6 cos V1. So we basically print that. We feed the model here to the sentence transformer, and we load the model, and then we get a bunch of statistics about the model information. So this is the model. The embedding dimension is 384. The max sequence length is going to be 512. So if we're feeding passages that have more than 512 tokens, then there's going to be a lot of information being compressed to turn that sentence into this vector length. And we are using CUDA. Total parameters 22 million, and the model size only 86 megabytes. So pretty tiny. So we're going to be doing the same test query that we saw before. So how do airplanes fly? And here we have some examples of test passages. And the very first one is actually the correct one. So airplanes fly because of lift generated by air following over wings. And then we have some ones that are some sentences that are completely unrelated, like pizza is a popular Italian food with cheese and tomato sauce. And Python is a programming language used for data science. And then this one is a little bit similar. The principles of aerodynamics explain how aircraft achieve flights, but I don't think it's as good as the first one. So we're just gonna print this, and let me go through the code. So we print this, we encode both of the query and the passages. So we feed the query into this list. The passages are read into a list of strings, so we just pass them here. The similarities we can calculate with the cosine similarity from PyTorch of those two vectors. So this is going to be a vector of 384 dimensions, and this one again with 384 dimensions, which just means it has 384 numbers in those vectors. And we're going to be calculating the cosine similarity between those two vectors. And here we're just doing some printing. So the score for each one of them, we can see that for the first sentence, the cosine similarity score was the highest with 80. And then it was 68 for the second sentence, which was still close but not as good. And then for the other ones, it was pretty bad. It still found, I guess, a tiny bit of similarity with the. I guess that is not even similar; it's 0.0. So yeah, so semantically related passages get higher scores even without word overlap, which is pretty cool. So what we're gonna do now is actually we're gonna do basically what we did for that example, we're gonna do for the entire passages and the entire queries that we have for our data. So we basically do this and it should take about a minute or so. I think for me, it ended up taking 55 seconds when I did it. So it's going to encode all of the 82,000 passages and all of the queries. And then here we have the passage shape. And then we do the same for the queries and we have the query shape. So 82,000 passages and each one of them is a vector of 384 numbers. And the query is 500 queries with a vector of 384 as well, because it's the same model, right? So, okay, we've done basically an information retrieval task previously with the example using cosine similarity. But another thing that we can do, we can use FIs for fast similarity search, which is pretty cool. And I've used FIs on embeddings before when I was doing plan play, which if you have embeddings, you can do so many things, so many useful things with them. Like I said before, you can train models on them, like linear classifiers. You can do cosine similarity. You can also run nearest neighbor search, which it's basically what FIs does, is this really fast nearest neighbor search algorithm that was created by Facebook. So FIS stand for Facebook AI. Is it AI or Facebook something search? Let me look it up. FIS. It's a Facebook AI similarity search. So yeah, it's an efficient similarity search and clustering of dense vectors. And it
I think
basically, yeah, you want to talk
Mila,
about it, Anthony?
no, like I think FICE is like we already went over this in a previous notebook, no? But I think you should kind of gloss over this because I think BM25 is a more important algorithm, especially
Okay.
for stage 1 retrieval. Because stage one retrieval is like you have millions or billions of documents. So doing like a dense retrieval is like super expensive. And
Hmm.
typically, like in practice, especially for like the kinds of experiments that we run, like you want to do a sparse keyword search in the first stage to narrow down the number of documents. Even though it's like less semantically precise, it's just way faster, like orders of magnitude faster than trying to do dense retrieval. And it's like more, the just indexing and searching is just more effective. Like this is like why Elasticsearch is a successful product, is because you're able to search over like lots and lots of like logs and data and documents using really efficient like sparse algorithms. But like yeah, I think it's good to just gloss over this. There's not a lot of time left in the hour.
Yeah,
So
I
BM25 is probably more important.
I didn't look into the time. Thank you very much. I thought we still had like 20 minutes. So yeah, I'm just gonna actually go straight to the BM25. So here we use FIS for similarity search. Let's keep going. Distribution of retrieval scores, analyzing retrieval distribution. We have narrow ranking, Y re-rank, and then PyTerrier. Okay, BM25. So like Anthony said, it's a very traditional keyword-based retrieval. Like I said before, that was one of the early things that came out to be. Um, and basically, just like Anthony said, it's a very much fast and efficient way of trying to retrieve documents that does not use those dense vector type of search algorithms. So basically how BM25 works, and if you have taken NLP, you probably have seen this. It's a sparse retrieval method that ranks documents based on the term frequency. So maybe you have heard of like TF-IDF, like TF meaning term frequency, how often a query word appear in the document length, and then the inverse document frequency IDF. So red words get higher weight. So for example, words like the and and on or with, those appear very often in the document, but they're not really important. Those are not like the words that you'd be looking for because they're so much predominant. So they would get a very low score. But the rare words, like for example, the ones that we are looking for, like airplane and fly and automobile, repair, maybe those are more important, so they get a higher weight. That's how I would kind of explain CF IDF. So yeah, so there's an example here. So how do airplanes fly? CF BM25 would score those documents by finding documents containing these words, weighing the rare words like airplanes more than the common ones, and then preferring documents where the query terms appear frequently. And it's much faster than FIs would be. Speed very fast, misses synonyms, which is like a drawback, but it's like one of the first steps that you do in a complex, I guess, information retrieval process, since it's a much faster algorithm. So here we basically just use PyTerrier to build a BM25 index. From the passages, we retrieve the candidates using the keyword matching, combine FIs for like a hybrid retrieval as a next step, and then we apply a narrow ranking to improve results. We have 5 minutes left, so I think I'm gonna stop here and just talk about the spring and just Thanksgiving, I guess. But I'm gonna leave the rest for you guys as a to do. And as you can see, there's a lot of code and it goes into evaluation. And yeah, there's like a lot of code into the notebook. And then at the end, you should get like this kind uh, of uh, of plots where we are basically comparing the pipeline with like BM25, FIs, Spark re-rank, dense re-rank, and a hybrid re-rank. And it seems that the dense plus re-rank is the one that scores the best across most categories, but some of them, even like recall, Sparse BM25 doesn't score too low compared to the other ones. But yeah, so some key takeaways here at the end again. And then there's some extensions that you can try to do. And I'm very much looking forward to seeing some of your PRs here. So let me go back to the presentation. Okay, so yeah, like I said, next week is Thanksgiving week. So we're not gonna have any meetings next Monday. I do encourage you guys to keep working on your research proposal drafts and to reach out if you have any questions. With that, I guess I can spend a little bit of time, I guess, just chatting about what we're going to be doing in the spring. So just to, I guess, emphasize once again, you absolutely do not need to take any 8903 to join us in the spring semester. Most people that do research with us do not take the 8903. And we will have a kind of interview approach this time into accepting everybody that will come to do research with us. So some things, if you are super interested in joining us in the spring, I would highly recommend that you actually do those exercises and actually submit the PRs when you do the exercises, because we do look at those thoroughly. At least I go through those one by one, accepting the PRs. So showing interest is really good. And yeah, keep an eye out for the interviews. We should probably start interviewing soon. And for that, I would recommend that you guys fill out the sign up form, the Clay 2026 competition sign up form as soon as you can. But with that, I think I'm gonna close here. Anthony, do you have anything else that you'd like to say that I didn't cover?
I think if you don't have anything to do for the Thanksgiving break, you could take advantage of just having access to Phoenix right now, and it's a good opportunity to, like, if you're interested in a particular play task, to download the data, and to do some like analysis on your own. The directory, like your user directories in that repo, are a good place to put code, just kind of any exploratory code. And that could be a really interesting thing to do. Like, you have access to GPUs, you have access to a pretty sizable amount of like compute. And it might, it's usually a good idea just to play around with, and take a look at the data. So I'd encourage you to try it out if you have the time.
Yeah, I second this. I think it's very valuable to just go into Pace and play around. And the more comfortable that you get with Pace right now, the better it's going to be in the spring semester. Also, it's probably going to help you with other classes if you ever plan to take like the deep learning class, or maybe even reinforcement learning, or even machine learning, that you probably do have access to Pace in some way. You just be super helpful for you to learn how to use it. So, and it's like free compute, so why wouldn't you want to use that? So super cool. Um, yeah, with that, I'm gonna close for today. It's 8:59. I think I do have a question here. Yeah, agreed. Reinforcement learning uses space in one of the projects for sure. Cool, awesome. If you guys have any questions, I'm gonna stick around, but yeah, feel free to drop otherwise. I wish a happy Thanksgiving for all of you guys, and I hope to see you guys on what dates? Let me go on the notes website to just check the date on the schedule. So we're gonna resume on December 1st. Wow, we're already in December almost. Cannot believe it. We're gonna resume December 1st, and this is gonna be when, this is actually good for me to say. The final research proposal drafts are gonna be due December 1st, so I totally oversaw that. So next time after the Thanksgiving break, it's when your research proposal drafts are gonna be due, and we're probably gonna be start to interviewing as early as possible. So keep an eye out for that. But yeah, with that, feel free to drop. Thank you very much for coming, and I talk to you guys later. Thank you.